Yeah, okay. So yeah, in the second part, so I would like to talk about something on the topological four groups. So I mean, you see the similar framework. So especially for the fiberized amenability. So and I plan to give the definition of that to make the fielder happy. So okay, so but what I will discuss is okay the theorem. So let me give it first. So so let your GB minimal. Okay. So of course, so topological principle. Second countable. Standard assumption on your group point. Of course, you have ample because otherwise your topological full group has a no meaning. Okay, so it's just you just have a trivial group there. So the ample so group point. Of course, so which is important, each fiber as a minimal. I will explain later. So each fiber as a minimal. Then your topological full group, I will define later. So isotic. So this is a result by using the fiber as a minimal. So okay, so we will talk. I mean, around this theorem, and we will see later. So this gives us a new framework to study the amenability of the topological full group in a counter dynamical system setting. So of course, everybody knows that. So that's at least a popular topic. Yeah. So okay, so what is a topological full group? Yeah. So which is only possible. I mean, which has only. I mean, has a, so the only case that it has a good definition is when your group is ample. Okay, so you just you consider all by.
Could you remind people what ample is for a groupoid?
Oh, ample just means zero dimensional. Yeah, it means
the object space.
It's the equivalent actually. So you have the compound open bisections as your basis for your group point. Okay, that's ample. So the good example to keep in your mind is the counter dynamical systems. Okay, so of course implement by the discrete acting group. Okay. So V is a bisection such that you are as V, your source of V equal your range of V equal the whole unit space. Of course, here we want it to be still we want this guy is compound. Yeah. And if your group is second countable, so this group is a discrete countable group. Of course, we do not want any topology on that. Even it is called a topological full group, but usually people just treat this as a discrete group. It's just because some historical reason. So if it is a second countable, your group is second countable. So this is also a countable discrete group. Okay. So then what is a fiberwise amenable? Is a fiberwise amenable. What I really want to say is that so on each fiber, each fiber gamma, so as gamma equal u, okay. Somehow you can put some length function, okay, exactly as you can do for groups, but you can do similarly on this fiber. You can make it a metric space, and in this metric space, you can define amenability. So that's exactly for the fiberwise amenability. So if you every fiber, so I mean there's at least the one fiber is amenable. So that means the fiberwise amenable. But we can show that if the G is minimal, then by translation, so actually so every fiber is amenable, especially in the ETL case, because the ETL means that so locally the geometric structure are same. Okay, that's the most important part. Okay, but equivalently, okay, it's a minimal. Okay, let me finish it. So, when somehow create okay GU as a metric space. Okay, so then
Wait, but isn't we're in the tau setting, so isn't the fiber discrete?
yes, but it also tell you that. So suppose this is your unit space, okay, and you have this is your fiber, yeah, fiber for you. But the utilities also tell you that you have a bisection as your basis for your topology of the groupoid, right? So then it will tell you you can choose a small neighborhood of the U.
Yeah, so that they're
And for other parts, so for other fibers, such that your unit is containing in the neighborhood U, the geometric structure are same with the, for example, you have V. Okay, V is very near to U. Then what you can show from the utilities is that in this neighborhood, V and the GV and GU are same. I mean, the geometric structure.
I mean that a discrete space is kind of like sort of boring as a metric space, no?
Discrete group, discrete space.
GU is discrete, right? Is a discrete.
Yeah,
space.
but we are talking about the cost geometry.
Okay, well, are you going to explain what kind of metric you're going to use?
Yeah, that's just a lens function, but that's take time to explain in this setting. Yeah, but somehow you can just think about like the group case. So that's a lens function, the metric induced from the lens function.
You need a minimal as a core space, as a core space.
Yes, exactly.
Oh, okay.
Yeah. So by the definition is due to like a Weinberger and some another. Oh, I forgot. It's a quite it's a paper quite long before, like in the 90.
I just thought there is a paper that can invite which was something about non-amenable one.
Yeah. As far as I know, so amenability for the cost metric space is introduced by
Okay, that's
One and the Weinberger. Yeah, that's yeah in terms. So
I think you also take some work on this.
yeah. He also did some work on this, but I mean the definition is introduced by that guy. Yeah. So Guolian also definitely did a lot of work here, okay, on the amenability of the metric spaces. Okay. Anyway, so but equivalency for groupoid, so the fiberwise amenability is just equivalent to say for any compact set K in G, okay, and for any epsilon, okay, bigger than 0, then you can find a finite set. Okay, it's finite in G. It may comes from the different fibers, but it doesn't matter. You can just choose from the one fiber. But anyway, so you can just find a finite set in G such that your KF minus this F, then over this F is not bigger than epsilon. That's similar things. All right, so
It's compact.
just a compact set in G.
But then what's cardinality?
No, KF is finite.
F is finite, but K is compact.
K can be infinity, but because your F is finite, so your KF is finite. Yeah, so this makes sense. So
Okay, I'm thinking about groups.
Yeah, but for groups, so K compact just means K finite. Yeah, same thing. So anyway, you have this one. So and you can define even a stronger version that your F is contain some. So a stronger version is you can find another compact set.
Sorry, I have another objection. So if you just choose epsilon KF is empty. Oh, I see, but then it's
Yeah, sure. One is not empty set. So.
but KF.
Yeah, it could be. It could be. But of course, so here you may want some non-triviality here. Yeah. So the stronger version is that you can there exists a C also compact G such that your F is contained in C. FU is contained in CU for any U in the G0. So if you replace there is a F is not infinity, it is not empty. By this sentence, you obtain a stronger version of the minimality, which is called the ubiquitous fiberwise minimality. And we can show that. So if your groupoid is minimal, so these two conditions are actually the equivalent. So by using the picture here, so because if your groupoid is minimal, so actually you can just use a finitely many small neighborhood to cover the whole space, and actually you don't have too many geometric type, because locally they're same. So anyway, so that's the fiberwise minimal, and then we can show this theorem. So I mean, of course, so because we have the fiberwise minimal, fiberwise minimality, then we can define the Foner size somehow. Then we can show this. Yeah.
I don't quite understand the conclusion. I would have thought that an interesting conclusion to a theorem would be that such and such a group is not so big.
Sure. Yeah. Sure. Definitely. Then if I can find some not so big groups, I will be so famous, right? So that's really impossible. Yeah. So yeah, I should say so. It's so big is not surprising. Yeah. But I will say so. Yeah, by the way, so I didn't give the definition of sophicity, so maybe should I give that? Yeah, okay.
Maybe you should first explain what our conversation just now. There are no known examples of a non-solving group.
Yeah, actually that's a very, very big question. So in the group theory. So
That's all that you need to know about that for this fault, right? You know about I mean, we don't need to know the definition of solving group because it will solve the problem and there is no information about it.
yeah, sure.
But doesn't one of Roman's favorite statements imply that there has to be a non-solving group? Because if all groups were solving, then it would only trivial statements.
Well, yeah, that's
If somebody finds the trivial thing, the whole thing.
but that's not a theorem. Yeah, that's just like a philosophy. Yeah. Anyway, so what does a solving mean? So let gamma be a discrete group. Of course, we usually want it to be a countable discrete group. So the gamma is a solving if for any finite set and for any epsilon, then you can find another finite set A finite, and a map theta from the gamma to the symmetric, the permutation group of A, such that so first, so this is just a map. This is not a group homomorphism, but the first condition is that so it is almost a group homomorphism in the following sense. First, I will explain what is Hamming distance later. So theta fg and theta f composed theta g is less epsilon. So if your f and g and f times g are in f, okay, or any where your Hamming distance of the two functions, maybe the alpha and the beta, is exactly you consider the ratio of the points that the alpha does not coincide with beta. Is that x in A, right? So and the alpha x is not equal to the beta of x, okay, over the cardinality of A. Yeah, so that's the first one. second one, so this means so this guy theta is no longer trivial. So that means for any f is not equal the identity map of the 1A. So then your timing distance of f and 1A is bigger than 1 minus epsilon. So it moves. So a lot of, I mean, the large ratio, large portion of the x in A. Okay. Third one, you can add this. You don't have to, so you can just arrange this. But I prefer to add this because it makes a lot of it makes I mean things easier to think. Okay. So just equal maps the trivial elements to the trivial function. Okay. So that's Sophic groups. So amenable groups are Sophic, residually finite groups are Sophic, and as George suggests, there's no known non-Sophic groups. So actually, so sophicity is a quite a weak condition for the groups. That's why it is very hard to find a counterexample. But even so, so it is usually not quite easy to verify a certain group has the sophicity. Okay. And so yeah, this is an example to show this. Okay. But suppose we have such a result, then what can we do by using such a theorem? So there's a combinatorial theorem due to the unluck. So but at first he just show that result for the residually finite groups, but then one forget. But anyway, he generalized to the Sophic groups. So gamma. Here's the theorem. Okay. So let gamma be finite, be a discrete, countable discrete group. Okay. Sophic group. So then gamma is amenable if and only if there is a so-called hyperfinite Sophic approximation maybe let's say AN. Okay. For your gamma. Of course, here we want countable finitely generated Sophic groups because you cannot define the Sophic approximation in a proper way. And so what does the Sophic approximation mean? It means now you take the sequence of Fn increasing to enumerate all elements in gamma, and then you suppose that's Fn. Okay. Then you take the decreasing epsilon, you denote by epsilon n, converging to 0, decreasing to 0. And such a pair, Fn and epsilon n, your Fn increasing, epsilon decreasing, then for such a pair, it will give you an. And then such an is called the Sophic approximation because it just approximates your gamma in some way better and better. Right, so that's the Sophic approximation. But why we need the finite generated? Because in this case, we can define a graph structure on the Sophic approximation in the following way. So your AN is equipped with a graph structure or even a directed graph structure. such that the vertices is just the AN itself. Okay. Now let's consider the edges. Okay.
The ANs are different to finite sets A.
Yeah, correct.
Okay.
Yeah. So and usually, so AN, the cardinality of AN is go to infinity. So because you want your F larger and larger, so you.
Okay, but in the definition of surface, well, they'll get larger and larger too.
Yeah.
Okay, well, I don't quite see, there's no evident difference yet. So what's up? Okay, well, the ANs are, whatever they are, they're different, they're directed graphs. But,
yeah. I'm trying to.
oh, you're saying these are disjoint?
No, I
No,
just
increasing.
no. I'm just saying. So I'm trying to define a graph structure on AN.
Yes, but is that the union? Or?
No. Vertex. The vertex set of the AN just AN. Yeah, and I'm trying to define the edges of the AN.
Okay.
Maybe I should change the notation to be.
Well, might be they're pointed at the bottom. That's all.
So it's just like the A, the theta. So now I should change it to be theta n, right? Because we have a theta n S A. Your A is in your AN, and the S is in a given generating set of your GAB. Okay, so this gives us a graph structure. Then actually explain what is hyperfinateness. So let's somehow look similar to what we have studied. Maybe you just be more familiar hyperfinite equivalence relation, but I mean anyway. So, but that's not quite the same. It has a following definition.
But where is the other one?
So this is due to luck. So let Gn be directed graph sequences. Okay.
Yes, it's capital S.
Capital S is gamma is generated by S. Just a generator of your group, right? That's why we need the your group is finitely generated, because we want the graph to be locally finite. Yeah. So be a direct, of course, so locally finite. No, actually, so even of the bounded degree, actually we need a bounded degree. So so each Gn is of a bounded degree. So Gn, the sequence is said to be hyperfinite. If for any epsilon, one can find a big number, k epsilon, such that you can always decompose each Gn into several pieces. So how many pieces doesn't matter. The point is that so the cardinality of each pieces is bounded by k epsilon. So that means so your Gn can be Vgn vertices can be decomposed as maybe E in. So I in some finite index set. So in such that your EIN cardinality is bounded by epsilon uniformly for n. Okay. Second, Now we consider, yes. Oh, so second, we consider the number of edges between this or among this EIN. Okay, so it's just like the no, like maybe the E. Let me. Okay, let me change notation. So maybe HIN. So HIN. So E, maybe the IJN is always defined to be the E, such that the origin of the E is in EI, and in HI. So the terminal of the E is in like the HJN. So it's in the EGN. Now you union every IJ. Then that's actually you obtain the all edges between this HIN. Right? So for example, this is H1N, this is H2N, this may be the HKN. So now I'm just counting the all bridges. Okay.
Question number 1. So since HIN is less than K sub epsilon, but where is epsilon? Instead of epsilon, there is a number K epsilon.
Yes.
But there is no epsilon anymore. Actually, not in subscript of K.
So K epsilon only depends on epsilon.
Yes.
And this condition is universally for all n. Yeah. That means for each n.
So epsilon is not a period.
No, it's at the
No,
very
no.
beginning.
Yes, but I mean, for epsilon, there is K epsilon, but then there is no epsilon anymore in the body of the statement. So I don't see.
Oh, because epsilon will appear in the second condition.
Okay.
Yeah. Okay. So then let's maybe be denoted by E prime to be the union IJ in the IN. Of course, your I is not equal J. EIN, EJN. So E prime is just the all bridges connecting the different islands, right? So now what we want is that, of course, so you should keep the N here. So lim inf, the N go to infinity. So this part E N prime, the cardinality over the whole the EGN. EGN because our graphs is of a bounded degree, uniformly bounded degree. So maybe bounded degree D. So actually, you can replace this guy by the vertex of the GN. So it's less than epsilon that you want. So this is called the hyperfineness. And you can see that so somehow it's related to the fauna. The faunality of the subset, right? So that means there exists some guy, some island, such that the edges is almost connected. Between the elements in this island, right? They do not have too many edges connecting to the other island. So that's the hyperfineness, and so the Alak and the another guy, I forgot his name, but anyway, they show that Alak showed this theorem for a relatively finite group, but then it was generalized to the general sulfate groups, okay, by someone else. Okay.
So somehow this pays tribute to the theory of the historical and theory of phenomenality, because that's where the word hyperfinite refers to. No, the word hyperfinite first appeared in the theory of phenomenality.
Yeah, but I at least at this moment I don't see any connection between.
Okay.
Yeah.
Well, okay, but there are a lot of things along the way.
Yeah, could be, yeah.
I mean, so if the person is in the first to use this word, then it has to be particular moment in time because that's a complicated word. The Greek Latin combination. But it's Murray and Feynman talked about an approximately finite 2-1 factor. He replaced that terminology in his book with hyperfinite. So, and the interesting thing is that hyperfinite includes being finite. So if you apply to an algebra, it only makes sense if it's finite in the first place. And then hyperfinite means it's approximately finite dimensional. But of course, the terminology evolved within Feynman algebra theory. It doesn't have to be a finite Feynman algebra to be hyperfinite.
Yeah.
But then equivalence relations, all kinds of stuff were called hyperfinite later.
Yeah. Yeah, but I just find so this notion, this hyperfinite notion is much more closer than hyperfinite equivalence relation. So, but
So is there explanation for hyperfinite translation?
at least
I don't see translation.
no, at least I cannot find one. But it's just from feeling. So
It's just some observation.
yeah, maybe. But I didn't say I will.
This word will never be in the dictionary unless it's a mathematical dictionary. But so if it gets used in a mathematical context, there ought to be possible traces. Otherwise, I don't think people are allowed to use terminology in a completely random way without any consent.
Yeah. I don't know. So
Yeah, I see the sense in this. Makes sense.
Well, that's like
yeah.
it should be possible to face it a little more concretely. Incidentally, I didn't I can't read the I don't remember what you said, but I can't read the letters coming after the word definition.
Alec or Alec. Yeah, Gabo Alec. Yeah, Gabo Alec.
And that's name, somebody's name.
Yeah.
E-L-E-K.
Yes. Yeah, E-L-E-K. So Gabo, Alec. Yeah.
Okay, well,
yeah.
Be interesting to see if he has any work more closely related to anyway, thanks.
Yeah. Okay. So so we have a clear, at least I hope clear picture. So for this theorem. So that means suppose you know a group is Sophic, and now you need to analyze the graph structure of the Sophic approximation. And suppose you can show this. Yeah, suppose you can show this, then actually you can show that your group is amenable. So and we all know that, so it is a quite interesting question. So when your topological full group is amenable, of course, necessarily your acting group has to be amenable. So
this definition reminds me of the definition of the standard. Related
yeah, beautiful. Yeah, for expander, that's true. It's quite from the definition, I believe it's a strong contradiction to the expander, because there has to be at least one island. The edge is almost all is just connect to the inside part. Okay, so we just apply that theorem to somehow to analyze this group. So that's how to use that. So even I should admit, so to show a group is Sophic is at least not so satisfied. Right? So we need to see whether your group has a stronger condition. So then let's go to the contour dynamic assessment setting, so which is a special case of the groupoid. So but anyway, so let gamma acting on X, okay, where gamma amenable group. Because if you want your topological full group is amenable, that necessarily your acting group has to be amenable. because this guy is a subset, a subgroup of your topological full group. Yeah. So it's no harm to assume it is amenable. And your X is simply the counter set. Okay. So what I have shown here is that, so no, at first, so if your acting group is amenable, so that means that you are associated a transformation group is fiberwise amenable. So it satisfies that the theorem. So by my okay. So so in this case, you are suppose your acting group, your action alpha is free, and the distal is a particular dynamical system. So studied by in that field here. So free distal, then your topological full group is indeed amenable. Okay, so what the method I used is exactly by combination. So this theorem and this theorem. So first, by that theorem, so even in this condition, so, we know that it is solving. Then we have to define or find the associated solving approximation, and by some I should say so quite a complicated calculation and the complicated combinatorial method, you can indeed show that. So if your action is a distal, then your solving approximation is hyperfinite. Okay, so then your topological full group is amenable. So so the earlier proofs based on so-called the extensive amenability of the actions. Based on some method of a random walks, okay, of the groups, but in this in my work, so I just use some combinatorial method instead of the random walks. Okay. So another application of this theorem, so if we go back to the topological groupoid, so we can show that so matrix almost a finite groupoid is fiberwise amenable. So therefore, for almost a finite groupoid, of course, minimal almost finite groupoid, the topological full group is solving. So before this theorem, so the matrix shows that so for minimal almost a finite groupoid, so the derived, you can say the commutator subgroup of the G is simple, but then we can strengthen this theorem by adding the sophicity for that. So another application, yeah. So let G be almost a finite minimal groupoid. Then the derived subgroup it's just equal to commutator subgroup. It's solving and simple. So strengthen one of the matrix results. Okay. Yeah, I guess yeah, that's a whole story. So maybe I'm earlier. So yeah.
Well, finite minimal groupoid is transitory.
What?
Well, if you have a group action, then it makes sense to say it's transitory. I suppose that that's a property of a group of an action of a group on a set that it should be transitory. Okay. Well, if you have a groupoid, I suppose it makes sense to say the groupoid is transitory.
Yes, somehow.
All right. Well,
yeah.
But my point is that if you say it's a finite minimal groupoid, it seems to me that's just another way to say it's transitory.
No, it's just, yeah, actually, so almost finiteness implies that.
You say, okay, you know, I didn't see the other A. I thought we were just talking about a finite minimal group, but you're saying it's almost finite.
Yeah, sorry, yeah, that's almost finite. In the sense of Matsui. Almost
Yeah.
finite, yeah. But actually, so yes, this tells that somehow your groupoid is free. It's essentially free, topological free. So transitive happens. Yeah. Oh, by the way, so also, so if you apply to some certain, I mean, concrete groupoid like the Penrose-Telling, that groupoid is almost finite. So therefore, the topological full group for the Penrose-Telling groupoid is solving. Yeah.
Question objection. So unless you need something, you don't give us any proofs.
Oh. Actually, so in last section, I gave a quite idea on the proof. But if you want, I can somehow give you this proof. So.
Well, I just
Yeah.
I wish that you organize talks so that there are more proofs with the talk, but they want with the definition of the definition of theories. So we didn't get to see any mathematics. No, I mean, proofs is mathematics.
Okay. Yeah. Okay, so let's show. Yeah, mainly because usually my proof is quite technical, so. So yeah. So let's show this. Okay, in the case of the counter dynamical system. So to give you some ideas. Okay, so let gamma acting on X. Okay, and now we want to show this guy is solving. So if you are acting, group is amenable. So actually, the first step is nothing but to show that your amenable group is solving. So you need to, of course. So here I mentioned, yes, we need topological principle. That means you need the topological freeness. So that means at least you can find one free point or one free orbit in your space. So choose such one. X, okay. Choose a free point. X, okay, and consider the partial orbit. So Fn times is X. So Fn is just a bonus set or bonus sequence. Okay, where is a bonus sequence. Okay, of gamma. Then
have a sequence of Kn of compact trends to get that answer defined for that. You can define what bonus set.
Bonus set here. Bonus set is just of gamma. Gamma is acting group.
Oh, it's a group.
Yeah. So I just try to explain everything in. Yeah. Because this could be messy to state. Okay. So we just look at this, and we want to define our map, right? Theta n from your gamma go to the symmetric Fn times X. So, but of course we will see that. So this is not good enough. Okay. But anyway, so that's I mean the idea at the beginning. In the following way, so of course you should give a F at the beginning, gamma in your topological full groups, and your epsilon is bigger than 0. Now define this. Of course, so F is a finite set of this topological full groups, and actually, so F can be translated into a finite set of your acting group gamma. That means somehow it just consists of finitely many group element, okay, as the call cycle. So if you know what that means, okay. So anyway, so then in the following way. So theta, oh sorry, that's not gamma, it should be. So theta n gamma, let me see. So it just go to let me see. So Sx is defined to be gamma is a homeomorphism, right, of your Sx. If your S is in I mean the phonon part, so it's gamma in this F, then gamma inverse of your Fnx. So that means because your S is no, sorry, Sx. Because your Sx is in this part, so your gamma times Sx is still in Fn times x. Because here we use the Fn is a phonon sequence. I mean, of course, you should make your n big enough to make everything phonon. So otherwise, you can just if your Sx is not in this part, of course, this should intersect with your Fnx. Fnx intersect with this, so it's not in. Sorry, I mean, why in this way? So Sx is in the Fnx minus this intersection, gamma in F, the gamma inverse Fnx. Okay, so by some particular bisection, okay, from this to I mean to the other remainder. So this is very standard. Some rho gamma x. It's just an arbitrary bisection. Yeah. Somehow you can define it this way. So suppose you define such a map theta n, and you want to where is my sophicity? Oh, I erased it. Or have we erased the sophicity? Okay, let me say again. Oh, but that not good enough for that. Yeah. So, but anyway, so what I want to say is that so there are several three conditions, right? So one is almost your map is almost a group homomorphism. Second, so your map is not trivial in a strong sense. Three is that it maps identity to the identity, right? So if you define in this way, the first one is okay. You can just try to verify. The third one is fine. But this one, no. You cannot do that because the point is that so the action of the topological full group on the space is highly non-free. It has a lot of fixed points, so that if your gamma, your Sx is not in support of the gamma, support means that it moves something, then you get a fixed point. So you don't have this. You don't have the second one. Second one means the theta, distance of theta f, the identity A is bigger than 1 minus epsilon. That means so theta f, if f is not trivial, it moves a lot of part of your A. Now your A is just this part. But because your gamma contains a lot of fixed point, so that means a lot of. It could be that it could happen that a large portion of Fnx not in the support of gamma. Then what should we do? So what we do is that we consider the product of this. So because we are considering the action from the minimal group, so we can be, and of course here we need the action is minimal. That means for any Clopin set, it has a non-empty Clopin set. The Banach density of that set is positive. So that means for the support of the gamma, and if your n is large enough, there is at least a very small portion, even small, but at least a positive of the Fnx located in the support of gamma, so that gamma will move that. And now you consider the direct product by enlarge this part. That means, so of course, so the action will be the diagonal action instead of the diagonal action will make that. So even for each one, you have the small portion, but you combine everything together, you have very, very large portion of the whole this finite space. And then by using this way, you verify this. So you have the sophicity.
For this density, you are using something like that.
No, it's Banach density. Banach density equal the infimum of the all environment evaluate on that. So, but because it is minimal, so then you are fine. But of course, you can just in this case you can replace the minimal by distal, because distal just means you can somehow can decompose your space into finite pieces, and each piece is minimal. Yeah, in some sense, yeah. So then you just combine finitely many this diagonal product. Then you'll be fine. Yeah.
I just looked up Gabor Illich, and he's definitely an operator algebraic. So, one thing he did recently was proven an analogous theorem to what Cohen, Feldman, and Weiss did with amenable, measurable, showing that they're hyperplane. Very deep. Illich did something similar to that in a uniform setting, more slightly different setting, different setting.
Yeah, that could be some connection, but yeah.
Anyway, you have to take on C-square algebra too.
Okay, I can look it up to see. So yeah, I hope that concept proof. Yeah.
Right, well, let's
Thank you.